हेलो। वेलकम बैक टू अनदर वीडियो। आज की वीडियो में हम एक और ब्लॉग वॉक थ्रू करने वाले हैं। तो रिसेंटली क्लॉड ने एक नया मॉडल लॉन्च किया है, ओपस 4.6। तो यूजिंग दैट सेम मॉडल दे क्रिएटेड सी कंपाइलर एंड इट इज़ मोस्टली वर्किंग। सो लेट्स वॉक थ्रू दैट। सो ये है ब्लॉग का लिंक. With title Building a Compiler with Team of Parallel Clouds. So this is recently published 2 days back. We have asked Opus 4.6 using agent teams to build a C compiler and then mostly walked away. Here's what it taught us about the future of autonomous software development. ओके, तो ये काइंड ऑफ एजेंटिक टीम्स बोल रहे हैं, तो यहाँ पे शायद मल्टीपल एजेंट शुड वर्क इन अ टीम. So this is article written by Nicholas Carlini, a researcher on our safeguard teams. Okay. So I have been experimenting with the new approach of supervisioning language models. We are calling team agents. Okay, where team agents, multiple cloud instances work in parallel on a shared code base without a active human intervention. This approach dramatically expands the scope of what achievable with LLM agents. Okay, to stress test it, I asked 16 agent with a writing a Rust-based C compiler from scratch capable of compiling the Linux kernel. Overall, nearly 2000 cloud code sessions and $20,000 in API cost. The agent team produced a 100K line compiler that can build Linux 6.9 on x86 ARM and RISC-V. I think these are architecture type of OS. This is a video. I am not going to play this right now. I'll play it later, but let's continue with the vlog. The compiler is an interesting artifact on its own, but I focus here on what I learned about designing harness for long-running autonomous agent teams, how to write tests that keep agents on track without human oversight, how to structure work so that multiple agents can make progress in parallel, and where this approach its calling. Enable long running clouds. Existing agent scaffold like cloud code require operator to be online and available to work jointly. If you ask for a solution too long and complex, the model may solve part of it, but eventually it will stop and wait for continued input questions and status update a request of clarification. हाँ, तो ये होता ही है जनरली व्हेन वी यूज एनी एजेंट एनी LLM मॉडल with our code bases, then it frequently asks us clarifying questions or um, multiple permissions to basically um, keep it working. To else sustained autonomous progress, I build a harness that sticks Claude in a simple loop. Okay, if you have seen Ralph loop, this should look familiar. When it finishes one task, it immediately pick next. Run this in container, not in your actual machine. ओके, तो बेसिकली इन्होंने कुछ तो सिंपल लूप बनाया है सो दैट ये क्लैरिफिकेशन और ये सारा पार्ट स्किप हो जाए. तो आई थिंक दिस इज द लूप कोड. वाइल ट्रू डू commit git rep parse short 6 head log file. This is maintaining some code. Claude dangerously skip permission p agent prompt.md model cloud opus. ओके, तो आई थिंक यहाँ पे भी आई एम नॉट श्योर ये क्या है, बट दिस लुक्स सम क्लाउड CLI कमांड to read from this agent prompt.md file and use this model and write it to some this log file. Okay, so in agent prompt I tell Claude what problem to solve and ask it to approach by problem into breaking small pieces, tracking what's working on, figuring out what to work on next to effectively keep going until it's perfect. On last point, Claude has no choice. The loop runs forever, although in one instance I did see Claude p kill 9 bash on accident, thus killing itself and ending the loop. Oops. तो बेसिकली ये एक आई थिंक इनफाइनाइट लूप है, बट समहाउ इसने अपने आप को ही किल कर दिया. Next is running Claude in parallel. Running multiple instances in parallel can address two weaknesses of single agent harness. One, तो जो दो weakness है उसमें पहली, the one Claude code session can only do one thing at a time. Yeah, makes sense. Especially as it has a scope of project expand debugging multiple issues in parallel is far more efficient. And second one is running multiple cloud agents allow for specialization, while few agent can be asked tasked to solve actual problem at hand. Other specialized agent can be invoked, for example, to maintain document, keep an eye on code quality, to solve specific subtask. My implementation of parallel cloud is a bare bones. A new bare get repo is created for each agent. A Docker container is spun up with the repo mounted to upstream. Each agent clones a local repo to workspace. When it's done, pushes from its local container to upstream. ओके, तो बेसिकली कैसे सेटअप किया हुआ है कि एक गिट रेपो सेटअप की है हर एक एजेंट के लिए, और एक सिंगल डॉकर कंटेनर स्पिन अप किया है जहाँ पे रेपो माउंटेड है टू अपस्ट्रीम, और सारे एजेंट क्लोन्स द लोकल कॉपी ऑफ वर्क स्पेस, देन व्हेन इट्स डन इट्स फ्रॉम लोकल कंटेनर टू अपस्ट्रीम. ओके, मेक सेंस. To prevent two agents from trying to solve same problem at same time, the harness uses simple synchronization algorithm. The cloud takes a look on the task writing file to current task. Okay, example, one agent might log current task parts if statement or text, while another logs current task code gen functionality definition dot text. If two agents try to claim the same task, git synchronization forces the second agent to pick a different one. ओके, तो यहाँ पे बेसिक सिंपल लॉकिंग मैकेनिज्म यूज़ की है टू अवॉइड picking up the same task. Cloud work on this task, then pulls from upstream, merges the changes from the other agent, pushes the changes, and remove the lock. Merge conflicts are frequent, but Cloud is smart enough to figure out that. The infinite agent generation loop spawn up a new Claude code session in fresh container and cycle repeats. This is very early results prototype. I haven't implemented any other method for communication between agent, nor do I enforce any process for maintenance of high level goals. I don't use an orchestration agent. Instead, I have level it up to each Claude agent to decide how to act. In most cases, Claude picks up next most obvious problem. When stuck on a bug, Claude will often maintain a running doc of failed approaches and remaining task in the Git repository of the project. Um, you can read through the history and watch it takes on the various task. ओके, तो यहाँ पे एक लुक ले लेते हैं. CCC Claude C compiler. Okay. Lessons from programming with Claude agent teams. The scaffolding runs Claude on the loop, but loop is only useful if Claude can tell how to make progress. Most of my effort went into designing the environment around Claude, the test, the environment, the feedback, so that it could often orient itself without me. These are the approaches I have found most helpful when orchestrating multiple Claude instances. Write extremely high quality test. Claude will work autonomously to solve whatever problem I gave it. So it is important that the task verifier is nearly perfect. Otherwise, Claude will solve the wrong problem. Improving the test harness required finding high quality compiler test suites, writing verifies and build scripts for open source software packages, and watching for mistakes Claude was making. Then designing a new test as I identify those failure models. For example, near the end of the project, Claude started to frequently break existing functionality each time it implemented a new feature. To address this, I built a continuous integration pipeline and implemented sticker enforcement that allowed Claude to better test its work to the new commit. Can't break existing code. Uh, okay, this is the first lesson. Second is put yourself in Claude's shoes. I had constantly remind myself that I was writing this test harness for Claude and not for myself, which meant rethinking many of my assumptions about how tests should be communicated result. For example, each agent is dropped into a fresh container with no context and will spend significant time orienting itself, especially on large project. Before even reach the test to help cloud itself, I included instruction maintain in extensive readme and progress file that should be updated frequently with the current status. I also kept in mind that fact the language models have an limitation, in which case needed to be designed around. These include context window evolution and time blindness. Okay, so what is context window evolution? The test hardness should not print thousands of useless bytes. At most, it should prevent few lines of output and log all the important information to a file so that cloud can find when it needed. Log files should be easily processed automatically. If there are error, cloud should write error and put the reason on the same line so that grep will find it. It helps pre-compute aggregated summary statics so cloud doesn't have to recompute them. Okay. Time blindness. Claude can tell the time and left alone will happily spend running hard tests instead of making any progress. The harness print incremental progress infrequently to avoid polluting context and includes a default fast option that run 1 to 100 percent random sample. This subsample is deterministic per agent but random across VMs. So Cloud still cover all the files, but each agent perfectly identifies the regression. Make parallelism easy. When there are many distinct failing tests, parallelization is trivial. Each agent picks a different failing test to work on. After test suite is reached 99% pass rate, which each agent worked on is getting different. Small open source project example SQLite, Redis, libjep, uh, to compile, but when agent started to compile the Linux kernel, they got stuck. Unlike a test suite with hundred of independent tests, compiling a Linux kernel is one giant task. Every agent would hit the same bug, fix that bug, and then override each other's changes. Having 16 agents running didn't help because each was stuck solving same task. The fix was to use GCC, an online known good compiler Oracle to compare against. I wrote a new test harness that randomly compile most of the kernel using GCC and on the only remaining files with Claude's C compiler. If the kernel worked, the problem wasn't in Claude's subset of the files. If it broke, then could be further refined by recompiling some of these files with GCC. This lets each agent work in parallel, fixing different bugs in different files until Cloud Compiler could eventually compile all the files. After this worked, it was started necessarily to apply delta debugging techniques to find pairs of the files that failed and together worked independently. Multiple agent roles. Parallelism also enable specializations. LLM written code frequently re-implement existing functionality. So I tasked one agent with the co-scaling any duplicate found in it. I put another in charge of improving performance of the compiler itself, and third I made responsible for outputting efficient compiled code. I asked another agent to critique the design of the project from the perspective of a Rust developer and make structural changes to the project to improve overall quality. Another worked on documentation. Okay, so different roles for different agent. Stress testing the limits of agent teams. This project was designed as a capability benchmark. I'm interested in stress testing the limit of what LLM can barely achieve today in order to help us prepare for what model will reliably achieve in the future. I have been using C compiler project as benchmark across the entire Claude 4 model series. As I did with prior project, I started by drafting what I want to be from scratch optimized compiler with no dependencies, GCC compatible, able to compile in the Linux kernel, and designed to support multiple backend. While I specified some aspect of design, I did not go into detail how to do it. Previous Opus 4 model were really capable of producing functional compiler. Opus 4.5 was the first to cross the threshold and allow it to produce functional compiler, which even could pass large test suite, but is still incapable of compiling on really large projects. My goal with Opus 4.6 was to again test the limits evaluation. Okay. Over 2000 cloud code session across 2 weeks, Opus 4.6 consumed 2 billion input tokens and generated 140 million output tokens. It cost just around 20k dollar compared to even most expensive Cloud Max plans. This was an extremely expensive project, but in total is fraction of what we would cost me to produce this myself, let alone an entire team. This was a clean room implementation. It depends on the Rust standard library. The 100k line compiler can build a bootable Linux 6.9 on x86 ARM and RISC V. It can also compile on different open source project and has 95 pass rate on most compiler test suite, including GCC torture test suite. It also passes the developer ultimate litmus test. It can compile and run Doom. The compiler, however, is not without limitation. These include it lacks the 16-bit x86 compiler that is necessary to boot Linux out of real mode. For this, it calls out GCC. It does not have its own assembler and linker. These are very last bit that Claude started automating and are still somehow buggy. The demo video was produced with GCC assembler and linker. The compiler successfully built many projects, but not all. It's not yet to drop a replacement of real compiler. The generated code is not very efficient. Even with all the optimization enabled, it output less efficient code than GCC with all the optimization disabled. The Rust code quality is reasonable, but it is nowhere near to the quality of what expert Rust programmer would produce. The resulting compiler is nearly reaches the limits of Opus ability. I tried hard to fix several of our limitations, but it wasn't fully successful. A new feature and bug fixes frequently broke the existing functionality. As one particularly challenging example, Opus was unable to implement 16-bit x86 code generator needed to boot into a 16-bit real mode, while compiler can output correct 16-bit x66 via 66 by 67 OP code prefix. This resulting compiled output over 60 kb, far exceeding 32 kb limit, enforce the Linux instead. Claude simply cheats here and calls out GCC for the space. Okay, the source code of the compiler is available. Download it, read through the code, try it on your favorite C projects. I have consistently found the best way to understand what language models can do as it to push them their limits and then study where to start to break down. Over the coming days, I'll continue having Claude push new challenges. If you want to follow along with the Claude's continue attempt and addressing these limitations. Now, looking forward, each generation of language models opens up new ways of working with them. Early models were useful for tab completion in IDs before long models could complete function body from its doc string. The launch of Claude Code brought agents into the mainstream and enabled developers to pair program with Claude. But each of these products operate under assumption that user define a task, and LLM runs for few seconds and minutes and return the answer, and then user provides a follow up. Agent team shows possibility of implementing entire complex project autonomously. This allows us as a user to use these tools to become more ambitious with our goals. We are still early, and fully autonomous developments come with the real risk. When human sits with cloud during development, they ensure consistent quality and catch errors in real time. For autonomous system, it is easy to see test passes and assume the job is done when it is rarely the case. I used to work in penetration testing, exploiting vulnerabilities in the products produced by large companies, and the thought of programmers deploying software they have never personally verified is a real concern. So while this experiment excites me, it also leaves me feeling uneasy. Building this compiler has been some of most fun I have recently, but I did not expect this to be anywhere near possible so early in 2026. The rapid progress, both language models and the scaffold we use to interact with them opens door of writing enormous amount of new code. I expect positive application with the outweigh the negative, but we are entering the new world which we will require new strategies to navigate safely. Nice. एक वीडियो और है इसमें. I think this could be the demo. Hmm. So I think this is the future, autonomous development with agent teams. Nice. तो यही था आज का ब्लॉग. आई होप यू लाइक इट. सी यू इन द नेक्स्ट वन.